So in the previous screencast, we learned about conjugate acid-base pairs and that the concentration of H3O plus and the concentration of OH minus are really important in determining if something is acidic or basic. Water undergoes a process called autoionization, right? And this reaction is always present in water where basically two water molecules react and one acts as the acid and one acts as the base. And they produce just a little bit of the hydroxide ion and just a little bit of the hydronium ion. Now, what we can do is we can calculate exactly how much this is. And it's not very much. It's 1 times 10 to the negative 14th equals the concentration of that hydroxide ion multiplied by, and I said hydronium there, hydronium ion multiplied by the hydroxide ion, okay? And so because we know this value and these two equal each other at a given temperature, if we know one and we know this value, then we can figure out the other. And this is really helpful. This can help us figure out the pH of certain substances and help us determine if something is acidic or basic. So let's talk a little bit more about if something is acidic or basic or not. So we talked about hydrochloric acid before, and we said, look, this hydrogen out here out front, or proton, indicates to us that it's an acid. But in a solution, when we start to look at that, an acidic solution is really defined as one that has more hydronium ion concentration than hydroxide ion concentration. So what we see then is because the hydronium ion multiplied by the hydroxide ion is 1 times 10 to the negative 14th, an acidic solution has more H3O plus, or H plus, right? Remember, those are used as synonyms. A neutral solution has equal amounts, okay? So that's a neutral solution. Water's a good example of that. Or sodium hydroxide, for example, right, is one of the bases that we talked about, and it's going to have more hydroxide ion in solution than H3O plus ions in solution, okay? And so that would be considered a basic solution. Now, one of the ways that we deal with, I want to point something out to you. When we look at this chart, you're going to see the hydronium ion concentrations here and the hydroxide ion concentrations here. And these are really unwieldy numbers. And so one of the ways that we can take really unwieldy numbers and make them more manageable is to use a log function, for example. So pH is called the power, pH is how we measure acids and bases. And I wanted to be able to tell you what pH stands for. And so in different sources say different things. Some say, well, nobody really knows. Others say it's the power of hydronium. So take that for what it's worth. So pH equals negative log of the concentration, which we use brackets for, of H3O plus. Now, I want to talk about concentration for just a second. Concentration is just going to be the amount of substance per volume. We're not going to calculate this, but you do need to be able to recognize that the unit here is a capital M, and that stands for molarity. Okay, and that's, again, just the amount of the substance per liter of solution. Okay, and so in this case, it's the amount of H3O plus per liter of solution. So if you have more H3O plus, right, your molarity is going to be higher. So we can calculate pH using negative log of H3O plus. We can also calculate the power of hydroxide ion, POH, by taking the negative log and the concentration of the OH minus ion, which are shown right here. And so one of the things that you'll notice is that for every solution, for example, let's look at tomatoes, right? Tomatoes have their hydroxide ion is approximately 1 times 10 to the negative 10th. Their hydronium is 1 times 10 to the negative 4th. When you multiply these together, that equals 1 times 10 to the negative 14th. When you put the hydroxide ion here, pH equals negative log of 1 times 10 to the negative 4th, you get 4. Try it. Make sure your calculator is working, right? When you calculate the pOH, you put 1 times 10 to the negative 10th in here, you get 10. When you add these two together, that gives you 14. This gives us a new beautiful relationship, which is pH plus pOH equals 14. And so it's a way for us to figure out what something, let me think. It's a better way, it's an easier way a lot of times for us to figure out the pH if we know the pOH, or the pOH if we know the pH. Now, I want to bring something up here. If pH is less than 7, it's acidic. If pH equals 7, it's neutral. And if pH is greater than 7, it's a basic solution. And so one of the things that's really helpful for us as far as pH is it's pretty easy to measure. There are a lot of different tools to measure pH. As I mentioned on the first screencast, we could use acid-base indicators, and basically these just change color based on the pH. So when we look at this acid-base indicator here, what we see is at a low pH it's red, at a neutral pH it's orange, and then at a basic pH, 9 and 10, it's yellow. So that's a really nice indicator. A lot of pools use these, if you've ever done any pool management, right? And so depending on the indicator, that gives you different colors. Phenolphthalein, for example, goes from colorless to a dark pink. Bromothiamyl blue goes from a yellow to a green to a blue. This was methyl red at the top. Now, pH meters are used for really accurate measurements, and the electrodes indicate small changes in voltage, and that's how we detect the pH of a solution. So for example, this is a very old pH meter. There's some much nicer, newer ones now. But basically you detect the change in the voltage, and that tells you what the pH is. We also have pH strips, which are something that can help us figure out the pH as well. Now, all of these relationships are really helpful because that means there's lots of different ways to calculate pH. And so this kind of gets to be a choose your own adventure at some point. So there's a lot of times multiple ways to solve the same problem. I like this slide because it helps you with relationships. So if you're trying to calculate the pH and you have H3O plus, right, you need to use the pH equals negative log of H3O plus equation, okay? If you have the pOH and you want to calculate pH, you use this equation. We're going to do an example of that in a second. If you have the OH minus concentration, you can calculate pOH using this equation, which we talked about previously. And then if you have H3O plus, you can calculate OH minus using this equation, and vice versa. So this is a really nice way to figure out a lot of different things, okay? So let's go and do some examples. So our first example is, what is the pH of a solution that has a pOH of 12.1? Now, the way these screencasts work is I can't go back, right? But you can look on the previous page. And when you look on the previous page of your notes, what we're looking here is we're trying to go between the pH and the pOH at the very top of that spreadsheet, okay? Or not spreadsheet, the very top of that diagram. So the very top of that diagram says, look, pH plus pOH equals 14, okay? Now, I'm trying to find the pH. That's what this is asking for. And so I know that pH equals 14 minus the pOH, right? I've just subtracted pOH from both sides. And so I can just plug in 12.7 for my pOH concentration, and now I have the pH, which is 1.3. And that's it. So that relationship is really helpful when we're trying to solve either the pH or the pOH, given one or the other. Now, another type of question that you'll run into is, what's the pH of a 0.040 molar, or molarity, that's the capital M, solution of HClO4. When you run into this type of question, you're going to use the pH equals negative log, and you're going to use the concentration of the acid. And brackets mean concentration, right? And so we're going to just take and plug in the 0.040 molar for the H3O plus. And when you do this using your calculator, you get 1.40. Okay. Another type of problem that we can run into is what's the pOH of a solution that has a hydroxide concentration of 2.6 times 10 to the negative 7. Well, now we have pOH, and we're given hydroxide concentration, and we know the relationship between pOH and the hydroxide concentration is pOH equals negative log of the concentration of OH minus. And so what we do is we say pOH equals negative log, and we plug in the concentration here, which is 2.6 times 10 to the negative 7th. We'll put that in our calculator, and we get 6.6 as our pOH here. And then finally, or the final kind of example I'm going to do here is what's the pH of a solution that has a hydroxide concentration of 3.4 times 10 to the negative 6 molar. So when we do this, right, we're asked for the pH, but we're given the hydroxide concentration. So with the hydroxide concentration, I can only calculate pOH. We just did that on the previous slide. We know it's negative log of 3.4 times 10 to the negative 6 molar. Okay. So we do this in our calculator, and that gives us 5.5. Now that's the pOH, but we're asking for the pH here. The very first example we did said, hey, look, pH plus pOH equals 14. And so now we're trying to find the pH. And so we just rearrange the equation. So pH equals 14 minus the pOH. That gives us 14 minus 5.5. And when we do this, we get 8.5 there. So lots of different ways to calculate pH, pOH, and we will continue to do some of these problems in class. And of course, you can always come to my office if you have questions.